Why is the parallel transport of vectors so important to general relativity? Well, this video deals with the concept of the parallel transport of vectors in space-time by using an example to help demonstrate the points I'll be making, and then goes on to show how it leads to the geodesic equation. Now let's go back to Newtonian dynamics and particles moving under Newtonian forces, in the presence of forces or the absence of them. And in particular, Newton's first law states that an object will remain at rest or in a state of constant velocity unless acted upon by some net force. So let's say we have a particle that travels along a straight line, the red one here. Now the particle's position vector is given by x is x1, x2, x3 coordinates. They're parameterized in terms of the parameter t, which could be time, often is, but it doesn't have to be. Could be some other parameter. And we'll just stick to the two-dimensional case just to make the image look simple. And so we have x of t, y of t, z of t will be 0. So this curve here, parameterized in terms of the parameter t, has x equals t, y equals t. So t equals 1, you're at this point here, 1, 1. At t equals 2, you're at 2, 2, and so on. Okay, here t is going to be equal to greater than 0. Now, a free particle means that it is not subject to any net force, and so Newton's first law applies. So it will remain at rest, or it will travel in a straight line with a constant velocity. And because it has that constant velocity, it means the magnitude of the velocity is constant, and it also means the direction is constant. So the velocity vector is a fixed velocity vector that doesn't change direction. All right. So travel in straight lines, which means we can expect the velocity vector to be constant, which it must be, and means that its magnitude is constant and its direction is constant. So the velocity vector of the particle traveling along this curve is u, is dx dt, the total derivative with respect to the parameter t, ddt of the vector t0, remember 0z component, to keep things simple. So we have, when we differentiate that with respect to t, we have a constant velocity vector with x component 1, or second component 1, and 0 for the third component in the z direction. Now this vector is tangent to the straight line. You can see with the blue lines here on the red one. Is tangent to the straight line along which the particle travels, and is of constant magnitude, which is easily verified. The magnitude of the velocity vector, or the tangent vector, is just square root 2 in this case, for this example. Now the interesting thing though is the velocity vector is clearly being parallel transported along the straight line. It is along this straight line here, it is tangent to it, but constant all the way along. Consistent with Newton's first law. Now we can use our example here to show that the velocity vector is parallel transported along the straight line in the positive direction without any change. Okay, now the condition for the constancy of this vector is that the total derivative of the velocity vector with respect to the parameter t is 0. So the velocity vector with respect to its parameter t is not changing at all. So du dt is 0. There is no change in direction. There is no change in magnitude. Okay, so u is 1, 1, 0 all the way along here. It's parallel transported along. A property of straight lines in Euclidean space, which is what we're in. Now, we can relate this condition to our original coordinates, xi of t, which made up the position vector. So the derivative of u with respect to the parameter t is the derivative of the position vector x with respect to the parameter t times the partial derivative of the velocity components with respect to each of the coordinates. This works out to be mathematically the velocity vector multiplied by this scalar quantity, the divergence of the velocity vector. Now, for this all to go to 0, we expect the divergence of the velocity vector to be 0. We expect that the velocity vector is not changing all along this curve here. There are no sources or sinks. And so we can say the divergence is 0 because we can pick any region on this curve here, And the velocity vector field entering it is the same velocity vector field leaving it. There are no sources and there are no sinks. So all along the curve here, the divergence is 0. So del dot u is this in the using the differential operator from Cartesian coordinates, which is what we're using, ddx, ddy, ddz, dotted with the velocity vector 1, 1, 0. When we carry out that operation, what we end up with, taking the scalar product, we end up the derivative of the first component with respect to x. Well, the first component is constant, so derivative of that is 0. Likewise for the second one and for the third. So the divergence here is 0. This tangent vector u, this velocity vector, its divergence is 0, and easily verified visually to simply just draw a circle around this region or draw a square or whatever shape you want around it, and then look at the vector field entering it, and it's the same. You can see visually it's the same as the vector field coming out of it. We don't expect there to be any change. There's no sources or sinks in there, and so this tangent vector, this velocity vector, is being parallel transported along our straight line here, along the path of our particle, as you'd expect with Newton's first law. Okay, now we have, so we can write that the derivative of the velocity or tangent vector u with respect to the parameter t is u times the scalar product del dot u. That's u times 0, which is 0, and we verified that that's the case for all in Euclidean geometry under Newton's laws. All particles not subject to any forces, that's free particles, will remain at rest or travel with constant velocity unless acted on by some net force. And so we expect that the derivative of the velocity vector with respect to whatever parameter we've used to parameterize it is going to go to 0. And that means the tangent vector or velocity vector has been parallel transported along the curve xit unchanged. Now we can write this in component form as duj dt is dxi dt duj dxi, or ui del I uj. Okay, notice the dxi and the dxi here both match, and then the independent, the one free coordinate is j. The free variable, the free index is j, and we sum over I. Now, where the del operator, del is the usual vector differential operator of the Cartesian coordinate system, which we're in. Now, the directional derivative operator for some curve xi parameterized by t is given by d dt as dxi dt d dxi. d dxi, xi refers to the coordinates xi of the curve. If we use some other parameter, lambda, instead of t, then we put a lambda down here. Okay, so far so good in Euclidean geometry with Newtonian dynamics. Next, let's have a look at Minkowski space now, and free particles, and they also remain at rest or travel in straight lines. And so let's take one such curve, its 4-position vector to be ct of tau, parameterized in terms of proper time tau. So I'm talking about a particle with mass here, because we can't use proper time for massless particles like photons. We'd use some other parameter such as lambda, but I'll deal with that at the end. For the moment, we'll just take tau, and parameterizing that in terms of proper time tau, we could have 3c tau, 3 times 10 to the 8 tau, 3 times 10 to the 8 tau for the x and y coordinates, 0 in the z direction again, so a bit hard to show on this diagram to have 4 dimensions. It'd be very, very difficult. So we'll just stick to the 3 time and 2 spatial ones. Now, tau, the proper time is going to vary from the negative here, referring to sometime in the past. This particle has a past, it's come from the past, and it's moving into the future. Okay, the fall velocity of this particle is tangent to its world line, and it's a constant vector, so we can see that by taking the derivative of the fall position. Okay, taking the derivative with respect to the parameter tau. When we do that, this tau, and this tau disappear, and we're just left with this vector here, which is each of the terms, each of the components are all constants in the z direction 0. Now, just pointing out here, why have I chosen 3 times 10 to the 8? I've just chosen to put a plot here, and each of the x, so 1 unit of x is 1 unit of x is 3 times 10 to the 8 meters, and it just makes the plot all look nice and even. Okay, this is plotted in terms of CT, so 1C, 2C, 3C, 4C, 5C, and so on. So T is still going in seconds, and X is going in units of 3 times 10 to the 8 meters. Now we can show that it must always be a constant vector. We can show that the fall velocity for a free particle in Minkowski space must always be a constant vector. Must have constant magnitude, and it will have constant direction. Okay, so a general fall velocity vector has the form mu is c dt d tau, dx d tau, dy d tau, dz d tau. That's measured by the particle, parameterizing its own path in terms of tau, its proper time. This is a particle with mass, an observer, a spaceship, whatever. Okay, for a coordinate for an observer far away, for a coordinate observer, if you like, it would be dt, d tau becomes gamma factor, and then dx d tau becomes gamma dx dt, coordinate time t for an observer observing the particle, gamma dy dt, and we can write that as gamma c ux uy uz, each of the components of the fall velocity. Okay, now the magnitude square, to show that it's constant, because we want to show that this is a constant vector, the fall velocity that is parallel transported for a free particle, not subject to any net forces. So the scalar product of the two of the fall velocity with itself, written down in terms of its basis vectors and components, is this object here, collecting the components to one side, leaving us the basis vectors. The scalar product of that gives us the flat space Minkowski metric, eta mu nu. Use that to contract the indices, and we get this object here, which then we write out the terms. We'll have a gamma squared out here because there's two velocity vectors here, so there's two gammas, and then we'll have minus c squared due to the with this metric I'm using minus plus 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 always on this channel, so signature plus 2, and expanding that out, we have this. Okay, in flat space, these two things are the same. This is just the velocity, the spatial part of the velocity squared, this object here. Okay, now gamma squared there, expanding that out, we'll have c squared on c squared minus u squared. Now here we're just going to factorize out a negative sign here. That turns this to c squared minus u squared. Top line, numerator, denominator cancel, we're left with just minus c squared. So the magnitude squared of the velocity fall vector is constant. It's the square of its magnitude, and also its magnitude is a constant. Different metric signature, -2 signature, that's -1, -1, -1, +1, would give me a positive c squared here. But the point is that the magnitude squared is a constant. So the magnitude of the vector is constant. The next thing we'll have a look at is direction. So what happens when it is parallel transported along some path? That's our next bit. But for all four velocities, they have, for a free particle, for all four velocities, we're going to have a constant magnitude. Okay, now the condition of parallel transport here is du d tau. Remember, this is a particle with mass moving, so we parameterized its path in terms of its proper time, measured by a clock it carries with itself, is dx, the position fall vector d tau, times the derivative, partial derivative of the fall velocity components with respect to each of the coordinates. So it's the same as in flat space here, that's Euclidean plus time, is still given by u times this scalar product del dot u is 0. Del dot u in this case, in the four-dimensional case, is this operator here. Okay, scalar product with that. Now these are all constant terms, and that all goes to 0. So the divergence is 0, again for the same arguments as for the Newtonian case. And so we can say u multiplied by this scalar product del dot u here is 0. The vector is parallel transported unchanged. So its magnitude and direction are not changing. In component form, we can write this du beta d tau is dx alpha d tau, du beta dx alpha is u alpha del alpha u beta is 0. For it to be parallel transported unchanged. Okay. Now, the directional derivative operating component form for Minkowski space is d tau is dx alpha d tau d dx alpha. And Minkowski space is flat space, so we can use the partial derivatives here. Our next stop will be to go to curved space, and that will no longer be appropriate to use the partial derivatives here. But we're still in flat space. In Minkowski space, Euclidean plus time is 4-dimensional space, 3 dimensions Euclidean, 1 dimension time. The partial derivative is appropriate. So if we had a second particle displaced from the first, but given the same velocity and direction, it will just follow a parallel path. Okay, and we can imagine any number of particles given the same velocity, same direction, but just dispersed throughout the region here, and they would each form paths which are parallel to each other. They neither converge nor diverge, so free particles travel in straight lines called geodesics, and geodesics parallel transport their own tangent vectors, which is what we've seen by the parallel transport condition. A second free particle traveling nearby with the same velocity will follow a parallel path that does not converge or diverge from that of the first particles, and you could have any number of particles doing the same thing. That will just follow parallel geodesics, which are parallel to the first one, parallel to each other as a result. Right, so geodesics in Minkowski space-time are straight lines, and these geodesics can form a congruence, and do form a congruence. Okay, now a congruence is a set of curves in some open region of space-time such that every point in that region lies on exactly one curve only, so that every point in this region can be covered by a geodesic and by only one geodesic that passes through that point. Okay, so there's no crossing of the geodesics. If there are congruence of geodesics, I mean there are other geodesics in other directions, you could have a congruence pointing in a different direction. But if I have this geodesic here, I can form a congruence by using infinitely many others parallel to it, so that the entire space is covered, so that every point has exactly one geodesic passing through it. Now we're going to go to the curved space. Now, what happens in general relativity dealing with curved spaces? We're finished now with flat spaces, so let's go. So let's start with an observer in a laboratory somewhere that is not rotating and is freely falling in a gravitational field of some source mass. So you can imagine there's an enormous mass somewhere, some Schwarzschild mass, somewhere, and the laboratory is freely falling towards it. Okay. Now, the motion of a freely falling object does not depend upon its mass or composition. The motion is determined solely by the mass of the source mass. Okay, that's the case in Newtonian dynamics, as well as here in relativity as well. So it's got nothing to do with the mass or composition. Okay, of the object that's falling is to do with the source mass. Within and close to this body, we effectively have a local inertial frame. Now, when I say within and close to this body, I'm talking about the laboratory, the observer and their laboratory, and a small region around it, okay, is a local inertial frame. So if the observer the observer here inside the laboratory throws a ball, it will bounce off the wall, okay. The Newton's laws apply to govern it. If the ball is placed in the air at rest, it will remain at rest. It's the whole laboratory, observer, and everything are freely falling together. It will remain at rest relative to the observer. If the observer gives it a push, it will move with a constant velocity. Or if the observer throws it with a bit of force, then all of Newton's laws apply. So it can remain at rest, it can move with constant velocity, and so on. It will accelerate for as long as the force is applied to it, and so on. So effectively, what's happening within the laboratory is you have a local inertial frame. Okay, so inside there, the observer, the ball, everything within it is freely falling towards the source mass, But within this laboratory here, what you have is a local inertial frame where Newton's laws apply. And we'll see the laws of special relativity apply. Okay. Now, the weak equivalence principle tells us that given a small enough region of space-time, we cannot distinguish by any experiment between the motion of a body due to gravitational effects from that due to it being uniformly accelerated. So you can imagine this laboratory sitting on the Earth. Everything is pulled towards the Earth. All observer, everything is standing on the base of the laboratory, but then and they would feel the force of gravity due to the body they're on, the Earth, what have you. Now, if that same laboratory is moved away from Earth, out into deep space, away effectively from any source masses, the observer there would not be able to distinguish between being at rest on the Earth or being accelerated uniformly in space. They would not be able to devise any test that would show them that there was any difference between being in a gravitational field on the Earth or being uniformly accelerated in space, far away from any mass. So acceleration due to some force would be indistinguishable to the acceleration they feel on the surface of the Earth as they're pulled towards the surface of the Earth. That's what the weak equivalences principle is telling us. We cannot distinguish between the two, between acceleration due to gravity and acceleration due to some other uniform force acting. Assuming, of course, the observer can't just look out the window, of course. So the freely falling laboratory must move towards the source mass, as we saw earlier. It must move towards it. There's no other possibility over it. It can't go fly. It's not going to fly off sideways unless some forces applied to it. So, but if no forces applied to it, it's freely falling, then that observer will just, and the whole laboratory, everything will fall towards the source of that field, the source mass here. I picked a Schwarzschild one here because I don't want any frame twisting or frame dragging near the surface here. It just makes the geodesics look very complicated. So I just want straight radial geodesics, straight looking, that is, radial geodesics. That's all I want. So in total, we have a free particle object in the form of a laboratory and observer, both moving in a locally inertial reference frame. Okay, so the observer in the laboratory, it's a local inertial reference frame, and for a small region around the outside of the laboratory, same applies. So that means they are traveling along geodesics. I'll show you a diagram that indicates what I mean. But okay, now locally the geodesics appear parallel, but globally that's not the case. As we saw in the previous slide, all the geodesics were converging towards the center of the Schwarzschild mass, or the source mass. We just pick two of those geodesics and follow them down to the center of the mass. You can see that if the observer in their freely falling non-rotating frame, freely falling towards the source mass, places two balls either side of the laboratory, then over time she will notice, the observer will notice that the balls gradually approach each other as time goes on. As the laboratory freely falls towards the source mass, the balls will get closer and closer. So globally, the observer would become aware that globally these geodesics are not parallel to each other as in flat space, as in Minkowski space or Euclidean space, but they're actually moving closer together. They're converging the further time goes on. So observing over a sufficiently long period of time, the observer will begin to notice the balls and everything within there starting to move closer together. So locally, the geodesics appear parallel, but globally, that is not the case. So the observer in the laboratory can detect the presence of a global gravitational field by the effect it has on freely falling objects over a larger region of space-time. Remember, over a small region of space-time, sufficiently small region of space-time, these geodesics will appear parallel, and the observer will believe themselves to be almost completely traveling within a local inertial reference frame, where the geodesics are all parallel to each other. So we see anyway, two balls released on the opposite sides of the laboratory will move together over time, indicating that the geodesics are traveling along are converging. Now, for this reason, Einstein proposed that gravity should not be thought of as a force, but rather as a manifestation of the curvature of space-time. Because as you remember, the observer in the laboratory here, with no windows able to look out, can't tell whether the laboratory is at rest on the surface of some body of mass m, or whether it's being accelerated in space somewhere, giving it a sense of being in a gravitational field. Can't tell, because if this laboratory has been accelerated upwards, far away from any source mass, then the observer will feel pulled towards the floor here, and so will the balls, and so will everything else, and they will feel like they were standing somewhere in a gravitational field. And because you can't tell the difference between uniform acceleration and acceleration due to gravity, Einstein proposed that gravity should be thought of as a force, rather not as a force, sorry, but rather as a manifestation of the curvature of space-time. And these balls moving together, this geodesic convergence, is the indicator that it's not so much a force as it is a property of the curvature of space-time. So having a look at it, is our laboratory far away from the source mass up here. Okay, so for this region here, including laboratory and some of the space-time around it, and the closer this region is to the source mass, the smaller this region will be. Okay, the smaller it will be, but the further away from the source mass laboratory is, the bigger will be this box, including region outside the laboratory. So for a small enough region of space-time, the geodesics will appear to be parallel to each other, and the balls will appear to travel in straight lines, or to remain at rest, or what have you, but they won't appear to be converging. Everything, as the laboratory falls towards the source mass, these balls won't appear to be moving in. But observe for long enough, and they will be seen to be, because clearly these geodesics do converge globally, but locally, for a small enough region, they appear pretty well parallel to each other, as though you're in flat space. So you are moving with a constant speed or velocity. So as though you are in a local inertial reference frame. Now, the equivalence principle, the strong version of it, refers not just to the trajectory of particles, but to all the physical effects that could be measured in laboratories. Can be stated as, within a sufficiently small region of space-time, the laws of physics governing a freely falling, non-rotating laboratory are those of special relativity. Now, a sufficiently small region of space-time means the further you are from the source mass, the bigger that region can be. But the closer you are, meaning the greater is the convergence of the geodesics, the smaller will that region be. All right. Now, they're not perfectly parallel. This diagram's a little bit off because it suggests they're perfectly parallel when they're not. But for all sufficient purposes, the convergence is negligible if measured over a small enough region of space-time. That's space and time. All right. Now, for some curve x of lambda, parameterized in terms of lambda, with and alpha is however many dimensions you're in, x alpha of lambda on a curved manifold, the directional covariant derivative operator in component form is given by capital D to distinguish it from the flat space operator. Capital D d lambda is dx alpha d lambda. So that's the derivative of the position vector components, the components of the curve with respect to the parameter lambda, times the covariant derivative, because we can't use the partial derivative now, we have to go with the covariant derivative because we're in curved space. Okay, so that's the covariant derivative operator. And the geodesic equation in component form is du beta d lambda is dx alpha d lambda, del nabla alpha u beta is 0. That's the covariant derivative of the velocity for vector, or the tangent vector. All that goes to 0, which is the geodesic equation, which tells you that the tangent vector for velocity vector is parallel transported along the geodesic. And to do that, it must satisfy this condition here. Okay, then this can be more nicely represented by u alpha del alpha u beta of 0. That's the geodesic equation. And that's the condition that tells you have an object traveling a geodesic. Its full velocity will follow this because geodesics parallel transport their full velocities. And there's not just the full velocity, but using the freely falling particle's momentum, which is just the mass times the full velocity, the geodesic equation can also be written in terms of its momenta, indicating that a particle's momenta points in the direction of the increasing direction of the geodesic, or the particle's momentum points in the direction in which it's moving. Okay, and that's that.